And the unicycling Murata Girl robot was back at Japan's C-Tech show with new tricks. Its biggest upgrade this year? Speed. The 2009 model can travel at 15 centimeters per second, triple the speed of the 2008 model. It can also handle curves with a diameter of 75 centimeters and ride over a balance beam just 2 centimeters wide.
Innovation, something that definitely would differentiate that space.
What if we could create something that could really function with humans and be useful? And so the outcome was this robotic system that communicates with you in your own language, figures out where you want to go, and actually takes you there.
SIGA stands for Santander Interactive Guest Assistance.
When the visitors arrive, they find this touchscreen console where they can choose a language and their destination. It can be a meeting room nearby, the auditorium, or the exit to the bus station.
It's Santander's very own family of robotic butlers that welcome me, help me to explore that building and amuse me.
This is probably the first application that uses swarm robotics in a commercial context. We normally see robots in factories or in research labs, but in this case we've developed a set of robots that function in a crowded space, 24/7, 365 days a year.
And when it comes to cutting the grass, have I got a welcome surprise for you all. Now here's something that's guaranteed to make you smile. Come here, Henry. Hello.
This is Boss, the car that won the DARPA Challenge of 2007 for self-driving vehicles.
The vehicle uses GPS and lasers and radar to kind of figure out where it is in the world and look out and see where the other cars are and how to drive safely around them.
Really, how does it avoid running over like my dog, say?
Well, so the GPS wouldn't tell you where your dog is, so it uses the lasers to look out and see where your dog is and tries to avoid it. And then we use lasers on the back of the vehicle to look down and see where the lane markings are. So as it's driving along, it can detect those and kind of center itself or register itself to the road.
So how long was this in development? This is a very complicated endeavor, I would imagine.
The actual Urban Challenge, this vehicle, we started working on about a year and a half ago. So we had about a year and a little bit before the race. So the challenge was a 60-mile race in a suburban environment. The vehicle had to be able to drive among other traffic. So on challenge day, there was 10 other vehicles out there with it, and 50 human-driven vehicles. It had to stop at stop signs. It had to yield for traffic. It had to be able to park. And it had to be able to do it all completely autonomously. That means without remote control, without somebody in it, making all its own decisions.
So how long until I can just kick back on the highway and let my own version of Boss, just do the driving. What do you think? 10 years, 20 years? How far away is that?
We think kind of from a technological point of view, it's about a decade out. So maybe by 2020, you'd be able to buy a car that has these features, maybe a subset of what Boss can do,
Right.
and get you between one place and another without you having to worry about it.
USC is part of the DARPA Learning Locomotion project. This project aims to push the performance of robotic legged locomotion to a new level. The locomotion controller, developed at the Computational Learning and Motor Control Lab at USC, is able to autonomously navigate and cross very challenging terrain, including obstacles and gaps as large as the full leg length of the robot. Special attention has been given to stability, smoothness, and movement speed, body movements that have been optimized for stable yet dynamic movements even in highly challenging terrains are combined with leg movements that avoid the terrain in an optimal fashion. This gives unprecedented movement speed over very difficult terrain, without sacrificing stability. The controller is able to employ special moves for terrain that approaches the limits of kinematic feasibility of the robot.
Blackjack, Urban QRF is on the way. Call sign Skywalker 2-1. Contact flight lead on button 5. Caesar's Palace, Blackjack, copy, he's all out. Skywalker 2-1, this is Blackjack. Blackjack, Skywalker flight is airborne. ETA to your pause is 8 mics. Transmitting final approach vectors now. Roger. Blackjack, Skywalker flight is 1 mic out. Roger that, Skywalker. Be advised, we are taking heavy fire from north and west. Multiple RPGs. Heavy machine guns in the area. We have 3 WIA. 20 total packs for extraction. Blackjack, Skywalker copies. Corpsman on board. Caesar's Palace, Skywalker 2-1. Caesar's Palace, go. Skywalker flight is clear. 3 WIAs on board. 1 Bravo and 2 Condition Charlie. Roger, Skywalker.
This video presents autonomous control capabilities for a quadrotor helicopter. We use a 20-camera Vicon system and an onboard IMU for state estimation. Here we show single, double, and triple flips. We developed a method for flying to any position in space with any reasonable velocity or pitch angle. We use the method to fly through windows at various angles. Here there's less than 3 inches of clearance on all sides of the quadrotor. We also fly between other quadrotors. The same method can be used to descend or ascend through a horizontal slot. We developed a claw-like gripper to enable the quadrotor to grab onto flat surfaces. We can pick up objects and release them on demand. A 0.2 kilogram structure is carried around a tilted circular trajectory with 4 quadrotors. The control method works for different numbers and configurations of quadrotors.
At FUMA Japan 2009, the International Food Machinery and Technology Exhibition, people's attention was caught by robots that handle food with hands just like people. Here, sushi is being carried by a sushi robot using a robot arm M430IA, manufactured by FANUC. The hand, which has a silicone skin just like a person's, moves the sushi between chopping boards. Here, Baumkuchen is being carried by a patisserie robot using a robot arm VS series from Denso Wave.
More difficult with this. Okay. Yes, good. Yeah. It's wonderful. Yes. Okay.
This video introduces the demonstration of skillful manipulation using a high-speed robotic system. The hand module has 3 fingers, a developed small harmonic drive gear, and a high-power mini actuator are used for each finger length. The hand can close the joints at 180 degrees in 1/10 of a second. The vision system consists of 128 by 128 photodetectors and an all-pixel parallel processing array. Using the vision chip enables various image features to be computed within 1 millisecond. This tactile sensor is a sheet-like object with only 4 wires. This sensor can measure the center position of a 2-dimensional distributed load and the total load within 1 millisecond. This is dribbling. High-speed active control enables the maintaining of a periodically stable motion. We call it dynamic holding. The dribbling period is around 100 milliseconds. This is pen spinning. The task is achieved due to the stability of objects experiencing high-speed rotation. The contact force and the timing of shifts about the axis of rotation are modified in real time by tactile feedback. This is throwing. The release method is designed so that the error of the ball direction is reduced. This is grasping a rice grain with tweezers. The tiny object is manipulated using a typical human tool. High-speed visual servoing enables the modification of force between finger and the tool. This is dynamic regrasping of a cell phone. This regrasping consists of throwing and catching, which contrasts with traditional methods that maintain contact state.